Hello students, in this video we'll see an example of changing a triple integral into cylindrical coordinates. Let's find the triple integral over region E of x times y plus 3z dv, where E is the region between the cone, z is equal to the square root of x squared plus y squared, and the paraboloid z is equal to 2 minus x squared minus y squared. So what does this region look like? If we draw the x-axis, the y-axis, and the z-axis, we have the cone that goes up like this. And then the paraboloid goes down like this. So we need to figure out where these regions intersect, where these graphs intersect. These graphs will intersect on a circle, like so, right? And so that circle is the set of points where the paraboloid intersects the cone. So how do we find that intersection? Well, this is our value of z on both of these surfaces, so we just set these equations equal to each other. Let's call this, we know that in polar coordinates this is r, so this will be a 2 minus r squared. So we're going to set 2 minus r squared equal to r, which is the same thing as saying r squared plus r minus 2 is equal to 0. I can factor this and say this is r plus 2, r minus 1 is 0. Now that tells me that r is either equal to -2 or r is equal to 1. But r cannot be -2, so this is going to force r to be 1. So in fact, these two surfaces intersect when r is equal to 1. So the area under which we're going to integrate is just going to be the unit circle. So that helps us with our limits of integration. So now, if we write down the limits of integration, what will happen? Since we know since this region occurs over the unit circle, the circle of radius 1 in the xy plane, I know that my angular variable theta goes between 0 and 2 pi, and my radial variable r goes between 0 and 1. Now, z starts where? Z starts on the cone, so z starts at r, because on the cone, z is equal to r, and goes up to this surface over here, which is 2 minus r squared. So I'm going to have a 2 minus r squared for my z limits of integration. So now we can change our problem into cylindrical coordinates. We'll have the integral from 0 to 2 pi for our theta. We'll have the integral from 0 to 1 for our r. And then my z will go between r and 2 minus r squared. I replace x with what? X is r cosine theta. Y is r sine theta. And then z is just itself, 3z. And we have an r. dz, dr, d theta is our Jacobian term for our differential volume element. Now, this looks fairly complicated, but what we know is that when we perform a z integration, so what will happen? Let's do the z integration over here. This will be the integral from 0 to 2 pi, the integral from 0 to 1. And then over here, I'll have an r squared cosine sine. That's actually going to be r cubed. So we'll have an r cubed sine theta cosine theta times z. And then over here, we'll have a what? We'll have a 3/2 r z squared. Z goes between r and 2 minus r squared. Then we'll have a dr d theta. Now, I claim that when we plug in these values, what will we get? So let's write this out. We're going to get the integral from 0 to 2 pi, the integral from 0 to 1. And then we'll have this whole term over here. Then I'll have z and the difference of those two. So we'll have an r cubed cosine theta sine theta. And then the difference of these, which is going to be a 2 minus r squared minus r. Then over here, we'll have a 3/2 r, and then we'll have a 2 minus r squared squared, and then minus r squared. Then we'll have a dr and a d theta. So now, when this is a function of theta times a function of r. So we can use box separation on that. But when we integrate cosine theta, sine theta between 0 and 2 pi, we're going to get what? We're going to get a sine squared of theta over 2 between 0 and 2 pi, and those limits will cancel out. So by using the fact that the trigonometric terms are going to drop out, this whole term over here, this whole integral term will drop out, and we're just left with this term over here. So let's think about what this is going to give us. So I have this 2 minus r squared squared. So let's algebraically simplify this term over here. That's going to be 3/2 r, and then inside the parentheses we're going to have a what? We're going to have a 4 minus 4 r squared, and then we'll have a plus r to the 4th, and then we're going to subtract that off from r squared minus r squared. So all total what we have over here. So this first term over here, so this integral is going to turn into the integral from 0 to 1. We'll have what? This first term over here is going to be a, well, that's going to be a 12 over 2. So 12, oh, so let's actually combine those. That's going to be a 5r squared. So it's going to be a 4 minus 5r squared plus r to the 4th. So the first term over here we're going to get is going to be a 6r. Then we'll have a negative 15 over 2r cubed, negative 15 over 2r cubed. And then finally over here, we're going to have a 3/2 r times r to the 4th power. That's going to be a 3/2 r to the 5th power, 3/2 r to the 5th power, and then a dr. And then we can easily integrate this. So this will integrate to 3r squared from 0 to 1. That first term over there is going to give me a 3. So I'm going to have a 3. Then this is going to be r to the 4th over 4. So that's going to be a minus 15 over 8. And then this will be a r to the 6th over 6, but 3 over 6 is equal to 1/2, so it's going to be a plus 1/4, right? So all total, what do we have? So 3, of course, is 24/8. 24/8 minus 15/8, and then plus 2/8. So we have 16 over here, so that's an 8. And so what do we have? We have 26. 26 minus 15 is 11, so we have 11 over 8 is our final answer. And then that was the r integral. So the r integral gave us this, and we have to multiply the r integral by the theta integral between 0 and 2 pi. So the final answer will be this over here times 2 pi from the theta integration. Thank you very much.